Finally, now let's use physics to solve this problem. Okay, so we can see that an orange is rolled across a 3-meter long rug. At this point right here, when it first reaches the rug, it's going 1 meter per second. So V0 is equal to 1 meter per second. And then it is decelerating at a rate of 0.01 meters per second, and since we have defined that as our positive x direction, that is actually negative 0.01 meters per second as the acceleration. So we can use the equation delta t is equal to v naught t plus 1/2 at squared. We can use that to determine how long it took for the orange to travel those 3 meters. So we set up the equation. The change of the displacement is equal to the initial velocity times the time plus 1/2 of the acceleration times the time squared. So plug it in and we get 3 meters equals 1 meter per second t plus 0.5 times negative 0.01 t squared. We can take that and put it into quadratic form, giving us negative 0.005 t squared plus t minus 3 is equal to 0. Solve that and we get an answer of 3.046 seconds, or an average velocity of 0.985 meters per second. Now, the interesting thing about this equation is that you can find the average velocity inside of it. If we break the equation into two parts, v naught t and 1/2 at squared, you can really see how this works. I think a velocity versus time graph is the best way to visualize this. We can see that v0t is the base of the figure, or the distance that the object would travel if it didn't accelerate at all. The initial velocity, or the height, times the time, or the length. We can then see that 1/2 at squared is actually the average increase in velocity, or the total acceleration, which is at, multiplied by 1/2, because there's two data points, one where there's 0 acceleration and one where there's maximum acceleration, multiplied by the time. So you get this kind of triangle figure. The first 100 meters of a 100-meter dash are covered in 2 seconds by a sprinter who starts from rest and accelerates with constant acceleration. The remaining 90 meters are run with the same velocity the sprinter had after 2 seconds. Determine the sprinter's constant acceleration during the first 2 seconds. The thing that sticks out to me here is constant acceleration. This tells us that we can use our delta x equation. The delta x equation is only applicable in times where the acceleration is constant and in 1D motion. So, we set that up as delta x equals v naught t plus 1/2 at squared. We plug it in, 10 meters for the displacement is equal to 0 meters per second, the initial velocity, multiplied by 2 seconds, the time, plus 1/2 the acceleration, which we're trying to find, times 2 again. When we solve this, we get that a is equal to 5 meters per second squared. Moving on to part B, determine the sprinter's velocity after 2 seconds have elapsed, we can look back to the delta x equation again. We can see that the equation for the total acceleration is equal to acceleration times time. You can see this in the units, where meters per second squared times seconds is equal to meters per second. So when we plug this in, 5 meters per second times 2 seconds is equal to 10 meters per second. So the sprinter was going 10 meters per second after the first 2 seconds. Moving on to part C. Determine the total time needed to run the full 100 meters. Well, we know a couple of things from previous information. First, we know that the first 10 meters took 2 seconds. Second, we know that the last 90 meters were run at a speed of 10 meters per second. So if we add 2 seconds plus 90 meters divided by 10 meters per second, we get 2 plus 9, which equals 11. So it took him 11 seconds to run those 100 meters. On D, when we're graphing this, we can see that the initial segment from 0 to 2 seconds is going to actually be slightly curved, because he is accelerating. However, after that point, he does not accelerate anymore, and the slope of the displacement versus time graph is linear.